Welcome to this presentation on the memory performance of AMD EPYC Rome and Intel Cascade Lake SP server processors. My name is Markus Velten. I'm from the Center for Information Services and High Performance Computing at the Technische Universität Dresden. We came at this subject from an HPC standpoint, and in HPC, x86 is still the dominant architecture. In recent years, the market share of AMD started to increase, especially thanks to the AMD Zen 2 and Zen 3 architectures, as you can see on the right-hand picture, the red-colored surfaces. The increasing number of cores in recent years led to increasingly complex memory architectures and general architectures, which is relevant, especially when considering that data placement and memory access patterns are relevant for the performance of many applications. This is even more true when considering that especially modern AMD processors are always almost non-uniform memory architectures, which we'll see when looking at the architectures in this detail. So AMD uses a multi-die architecture with a single central I/O die, which is connected to the 8 core complex dies, or up to 8 core complex dies, each of which hold 2 CCX, which have in turn 4 cores. The Infinity Fabric AMD uses connects the CCDs to the I/O die and to the I/O and memory interfaces. We have 8 memory channels in total, but there's no direct connection between CCDs, as you can see, and there's also no direct connection between the 2 CCX within a single within a single CCD, as we'll see later. This entire design looks like a NUMA architecture. So assuming a memory access from a core in the top left corner to its local memory in the top left corner will be faster than a memory access from the top left corner core to memory in the bottom right corner. 64 cores are available on these processors, and they use a modified MOESI coherence protocol using the states modified, exclusive, owned, shared, and invalid. For the cache lines, other states have not been publicly described by AMD. The Intel design is a monolithic one, using a 2D mesh that connects all components. This design is not necessarily a NUMA design, but can be configured to expose 2 NUMA nodes to the operating system via sub-NUMA clusters. We have up to 28 cores and a MOESI coherence protocol with states modified, exclusive, shared, invalid, and forwarded. The system has 6 memory channels in total. We use 2 test systems. The AMD EPYC Rome system is our own in-house HPC cluster. Access to the Intel system was provided by the Erlangen National High Performance Computing Center. The AMD system uses 2 64-core processors per compute node with 2 GHz nominal clock speed and main memory running at 1600 MHz, which is the fastest main memory you can use with them. Intel processors use two processors with 20 cores running at 2.5 GHz, and the main memory ran at 1467 MHz, which is the fastest main memory speed. Because the 2 systems were used from 2 different sites, they ran 2 different operating systems, but both were configured to expose NUMA nodes to the operating system. In case of AMD, 4 NUMA nodes per socket and 2 NUMA nodes per socket for the Intel system. We used as benchmarks written in assembler. The latency benchmark can be configured to access local memory as well as remote memory in all memory levels. And the throughput benchmark analyzes the throughput of SIMD instructions via the floating point units, which is obviously limited by the bandwidth of the caches or main memory. Therefore, we use that benchmark to analyze their bandwidth. With that, let's take a look at the local memory access latencies. So everything within the local core and the local main memory. We see similar L1 latencies for both processors, but the Cascade Lake processor has higher L2 cache latencies and L3 cache latencies. although there's a caveat to the AMD L3 latencies, which we'll see later. The main memory latencies are higher on the AMD system, simply thanks to the access to the I/O die, which is necessary for these memory transfers. Let's take a look at the cache bandwidth for cache and main memory accesses. We see that AVX instructions are able to utilize the theoretical L1 bandwidth. SSE comes very close. SSE and AVX almost saturate the L2 bandwidth, and the L3 bandwidth does not scale linearly with the number of cores. Only 3 cores out of the 8 of a single CCD are enough to saturate the main memory bandwidth. And with that, let's take a look at the Cascade Lake results. We measured these at 1.6 GHz, which is the nominal all-core AVX 512 frequency, so lower than the regular nominal frequency. All SIMD width were below their theoretical L1 cache bandwidth. So for instance, we measured 186 gigabytes a second L1 bandwidth for AVX 512, but expected 204.8. We have seen a significant L2 cache bandwidth drop for SSE and AVX. So take a look at the 87.3 gigabytes a second that we measured for AVX 512 and compare that to what we see for instance, SSE. So we would have expected to see identical L1 and L2 cache bandwidth simply because 46.5 gigabytes a second L1 bandwidth for SSE is lower than the 87.3 L2 bandwidth for AVX 512. We would have expected on the SSE side of things, on the AVX side of things, to see the exact same bandwidth as for the AVX 512 instructions, but this was not the case. The L3 bandwidth does not scale linearly as well, and 8 cores are necessary to saturate the main memory bandwidth on a single subNUMA cluster. With that, let's take a look at the remote memory access latencies on Rome. So everything was within the same socket. We see distinct NUMA characteristics. So the darker basically the color gets in these charts, the further away the NUMA node is, or the memory is. We see that we need about 150 additional cycles when accessing memory in a remote CCX. And this is particularly true if we take a look at the L3 results. We see the 39 cycles for everything that's local or local to the CCX. But once you start to leave the CCX and want to access L3 on another CCX, we see that additional 150 cycle penalty. Accesses to remote NUMA RAM take about 10 to 35 additional cycles. On the Cascade Lake side of things, we see that additional 5 cycles are required to access the most distant core in the same subNUMA cluster. Accesses to the second subNUMA cluster take an additional 15 cycles approximately, and the entire L3 cache is accessible for all cores with similar latencies. In general, although we configured non-subNUMA clustering, we see that this design does not really behave like a very clear NUMA architecture like the AMD architecture did. With that, let's come to the summary. The AMD EPYC Rome processor has very distinct NUMA properties. The L3 cache is effectively shared only on a CCX level, and we've seen a very high effective floating point throughput coming close to the theoretical limits. We've seen that a low number of cores can saturate the main memory bandwidth, which means that we have a high per core main memory bandwidth. The Cascade Lake processor, on the other hand, has no distinct NUMA design thanks to its 2D mesh, which means that the L3 is effectively shared among all cores with low latencies. We've seen that floating point throughput is below specifications for all SIMD width, and we've seen that a high number of cores is needed to saturate the main memory bandwidth, which means that we have a low per core main memory bandwidth. Let's take a closer look at some of the details of the architectures. So this is a picture of the layout of a single CCD. So you can see that it consists of 2 CCXs. and the Infinity Fabric on Package interconnect, which does not connect the two CCX directly to one another, but all data transfers have to be passed through the I/O die that happen between these two CCXs. Each CCX consists of 4 cores and 4 L3 cache slices, and each core has its own L3 slice, which is a victim cache, which holds evicted lines from the L2 cache, valid copies of shared lines, and shadow tags for cache coherence. The L2 cache is inclusive of the L1 instruction data cache, which are both equal in size. The load store unit is able to perform loads and stores with a width of 256 bits, which is relevant because the floating point units are 256 bits wide as well for AVX instructions. The predecessor, the Zen architecture, had to split AVX instructions into two 128-bit instructions simply because the execution units were only 128-bit wide. There are no distinct AVX frequencies on these cores, so they may throttle if they reach their power or thermal limits, but otherwise may run at dedicated at the nominal or even turbo frequencies. The per core L3 slice on Intel Cascade Lake processors is smaller compared to the AMD design. This is a non-inclusive cache, which may work as a victim cache. The L2 cache is bigger than that. On the AMD processor, we have 1 megabyte compared to 512 kibibytes. This is an inclusive cache that holds cache lines from the L1 instruction and data caches. Both of these are equal in size as well and have the same 32 kibibyte size as the AMD L1 caches. The load store units can perform these operations at 512 bits per cycle in order to support the AVX 512 units. AVX 512 instructions can be executed either by fusing the units on ports 0 and 1 into one 512 AVX 512 unit, or some models have an optional AVX 512 unit on port 5. This was the case on the processor we analyzed. These processors have dedicated AVX and AVX 512 frequencies. The nominal AVX and AVX 512 frequencies are below the nominal baseline frequency for this processor, and these nominal frequencies decrease once you start to use more cores. These are frequency ranges, so they have turbo frequencies as well. So this may be something you want to keep in mind when using these processors. So let's take a look at a couple more detailed results, starting with Intra-CCX latencies on the Rome processor. We performed the L1 and L2 axis analysis with 512-byte alignment, which led to a scenario in which only the L3 slice of core 0 seemed to be used. This exposed what seems to be a ring interconnect within the cores, because if you, for instance, look at the requesting core 0 on the x-axis in the L2 memory level, L1 memory level, and look at the latencies depending on the owning core, you can see that the first core 3, has a higher latency than those that seem to be closer by, which indicates to us that this may be a ring interconnect. Looking at remote socket latencies on AMD EPYC Rome, it shows us more of the properties of the I/O die. So in that picture, we've simplified that image a bit, showing only the XGMI or socket-to-socket global memory interconnect interfaces, which manage the socket-to-socket interconnects. And the arrows we've indicated here show the potential data transfer paths according to our measurements. And simply by looking at that, we can already make a couple of assumptions. For instance, the best case scenario would be if transfers happen between NUMA node 0 and 6 or NUMA node 2 and 4, simply because they have the shortest data travel paths. for these transfers. The worst case scenario, on the other hand, is a direct diagonal access from NUMA node 1 to 5 or 3 to 7, which is something that we can back up with numbers as well. So looking at the best case scenario here, you can see that this takes about 203 to 204 nanoseconds compared to the 217 or 218 nanoseconds used for the worst case scenario. So a penalty of about 13 to 14 nanoseconds when using the worst case compared to the best case. Overall, we have a penalty of about 100 nanoseconds when using a when having remote socket memory accesses. We dug a bit deeper on the main memory saturation on Rome using the stream triad benchmark. We've seen on a single CCX that 2 cores can saturate the bandwidth with that benchmark. We've furthermore seen that by using 1 core per CCX on a single CCD are enough to saturate the bandwidth for a single CCD. Going to the entire NUMA node with its 2 CCDs, we can see that 4 cores are enough to saturate the bandwidth, either by using 2 cores on only one of the CCXs per CCD, or by using 1 core per CCX per CCD. So 4 cores in total gives us the highest possible bandwidth we are able to measure on a single NUMA node. We were able to analyze the quartile layout on Cascade Lake, on the Cascade Lake system. For that, we used a method introduced by McAlpin. And this allows us to determine the position of the CPU IDs as exposed to the operating system as seemingly, or as increasing numbers do not necessarily mean that for instance, CPU 1 is a direct number of CPU 0. We use that to fine-tune our latency analysis to determine which cores are indeed close neighbors and which are sitting further apart. This analysis furthermore showed us that the third UPI link was not used for socket-to-socket communication. So only these 2 UPI links indicated in these pictures we used for that, which is something that McAlpin found as well in his analysis. This leads us to the remote socket analysis, a latency analysis on Cascade Lake. We have seen a approximately 60 nanosecond penalty for remote socket accesses on these processors. And we've seen that an access to the second sub-NUMA cluster on the remote socket led to a penalty of additional 10 nanoseconds. Summarizing these details, we've seen that the latency analysis can reveal the communication layout within a CCX. We've seen that there are fairly complex socket-to-socket communication patterns due to the I/O die layout. And we've seen that one can achieve higher main memory bandwidth when using 2 CCDs, which may be important if you're having workloads that rely on high memory bandwidth. A 64-core model may be more suitable for your workload than lower core tiers, simply for these additional CCDs and the additional main memory bandwidth. On the Intel Cascade Lake system, we have seen that we can analyze the position of the activated quartiles and the associated core IDs exposed to the operating system, which we used for our latency analysis and may be useful in general for performance analysis on these systems. We have furthermore seen that the remote socket latencies reflect the impact of the SOC-NUMID clustering, although we have seen a less complex communication pattern compared to the AMD system. And with that, I thank you for your attention.